In boxing, you've got punches that sting, and then you've got punches that turn the lights out. Today, we're going to break down the science of that knockout power. We're diving into the physics that separates a simple, pesky jab from a truly devastating cross.
Okay, so a cross hits harder than a jab. We all know that, right? But why, really? Is it just about twisting your body more and using more muscle, or is there some kind of hidden biomechanical secret that gives the cross its fight-ending power? That's the question we're digging into.
So first up, let's talk about our two contenders here. We need to make sure we're all on the same page about what these punches actually are.
On one side, you've got the lead jab. You can think of it as the boxer's rangefinder. It's quick, it's straight, and it's fired from that front hand. It's all about setting the pace and finding your distance. Then you've got the rear cross. Now this is the power shot. It's thrown with the rear hand, and it involves that full rotation of your hips and your torso. This one is designed to do some serious damage.
So that's the common wisdom anyway. But what does the hard data actually say? Well, researchers literally strap sensors onto elite boxers to measure everything. Let's take a look at the force, the speed, and the power.
And wow, the difference in pure force it's just startling. The research found that the average lead jab lands with about 1,177 newtons of force. Okay, but the rear cross? A whopping 1,709 newtons. That is nearly 50% more force. It's scientific proof of what every boxer already knows.
And listen, that's just the average. The peak force they recorded for a rear cross was an incredible 2,867 newtons. To put that in perspective, that's like taking over 630 pounds and concentrating all of that force onto the tiny tip of a glove.
And when you look at the data side by side like this, it's a clean sweep. The cross is superior across the board. The punch force is higher, the fist acceleration is way greater, and even the contact time is a little bit longer, which lets more of that energy transfer right into the target.
So, case closed, right? The cross is stronger because you put more of your body into it. More mass equals more force. Simple. Well, this is where the science throws a little jab of its own. It is not nearly that simple. Let's get to what they call the effective mass twist.
So first, what even is effective mass? The easiest way to think about it is like this. It's the percentage of your total body weight that you actually manage to get behind the punch at the exact moment of impact. It's basically a measure of how well you can get your whole body involved in the strike.
Now, with that huge power difference, you would totally expect the effective mass of the cross to be way higher. But what the data shows is absolutely fascinating. For the lead jab, boxers mobilize 21.5% of their body mass. Okay, so for the super powerful rear cross, just 21.0%. They are almost identical. So the extra power is clearly not coming from throwing more of their body weight into it.
And that, right there, that brings us to the real puzzle. This is the big question. If these elite boxers are committing the same percentage of their body weight to both punches, where on earth does all that extra fight-ending power in the cross actually come from? So, to solve this little mystery, we have to look past mass. We have to see what the analysis revealed as the true drivers of power. Let's find out what really makes a punch powerful. The statistical models pointed to three key things. First, total body mass. No surprise there, right? Heavier fighters tend to hit harder. Second, training tenure. Basically, experience. The more you practice, the better your technique gets for generating force. But the most critical factor, the real key, was fist acceleration. The data showed a really strong direct link. The faster your fist accelerates, the harder it's going to hit. This is the secret sauce.
But there's a catch, and this is so cool. The study found a fascinating trade-off. There's this inverse relationship between acceleration and effective mass. In other words, the more you focus on pure speed, the less of your body mass you can effectively get behind the punch. So the most powerful strikes aren't just about maximizing speed, and they're not just about maximizing mass. They're about finding the perfect biomechanical balance between the two. So if acceleration is king, how is it generated? Well, the answer is in something called a proximal to distal sequence. The best way to picture it is to think of cracking a whip. The power starts in the large parts of your body, close to your core, your torso and upper arm. Then that energy flows down the chain to the forearm, and finally, it's all unleashed through the fist. The rear cross is so much more powerful because that full body rotation creates a much longer, faster, and way more effective whip.
So what does this all mean for athletes and for coaches? Let's try to translate this science into smarter training for stronger punches. The takeaways here are actually pretty clear. Power isn't just about hitting a heavy bag harder. It's about focusing on drills that maximize your fist acceleration. It's about optimizing your body mass with smart strength and conditioning. But really, above all, it's about training for whole-body coordination to perfect that kinetic whip, making sure energy flows seamlessly from your feet all the way to your fist. And that's the kind of technique that experience really hones over time.
You know, the researchers themselves put it best. They said, quote, "Effective utilization of the entire body could lead to the highest force values being achieved." So knockout power, it isn't born in your arm. It's a symphony of movement that starts all the way from the ground up.
Which leaves us with this final thought. Is the secret to true punching power found not in the size of the muscle, but in the perfection of the sequence? Is it less about brute strength and more about that flawless, lightning-fast transfer of energy through the body? Well, based on the science, the answer seems to be a resounding yes.